Let's begin to explore some of the less obvious yet incredibly useful applications of nuclear. We all love food and indeed need it to survive. Most fresh foods, however, are perishable and only last a few days before going off, even if they're refrigerated. This is certainly annoying, especially when you open the fridge to find what you're looking for is covered in mould or smells funny, but it's also undesirable in terms of waste, both of the food and the money you spent buying it. Radiation is often seen as something that can only be harmful, however, it can be very useful. A classic example of how it's used in the food industry is to prolong the shelf life of strawberries by irradiating with gamma rays from a cobalt 60 source. The radiation destroys the microorganisms and the parasites responsible for spoilage, such as mold spores or bacteria cells, and also kills the parasites that may be present, especially in fresh foods. The advantage is that the food product itself is not damaged in any way, unlike as it would be, for example, if heat or steam were used. It's important to emphasize, though, at this point that just because food is irradiated does not mean that the food is radioactive and in any way harmful to eat as a result. It's reckoned that similar methods are used to treat around 500,000 tons of food across 60 countries each year. Shortages of fresh, clean water is a global problem of gross proportions. Today, 663 million people lack access to safe, clean water, and by 2025, it's estimated that 60% of the world's population is too at risk of being deprived of this basic human right. One way of solving this problem is to make use of groundwater, which is water stored in porous rocks in the Earth's crust. Thanks to the presence of radioisotopes in this water, including carbon-14, krypton-81 and chlorine-36, we can use imaging techniques to map where these water sources are and the volumes they hold. In addition, we can also use radioisotopes of carbon, hydrogen and oxygen as tracers to monitor potential pollution and contamination of these sources. As we mentioned in the third video of this series, called Types of Radiation and Their Properties, any ionizing radiation has the potential to damage cells and their DNA, which may result in mutations and the growth of cancer. As much as this is a problem, we can also use nuclear medicine to diagnose and treat diseases like cancer. Technetium-99m, M if you're interested stands for metastable, is used over 40,000 times a day to diagnose organ abnormalities. How does it work? Well, technetium-99m is absorbed by biological tissues, notably the heart, brain and liver, and the gamma radiation it emits can be detected by scanners to generate maps of internal organs. You might think that the last thing you want to do is ingest a radioisotope. However, as its half-life is only 6 hours and the amount prescribed is so small, it doesn't last long in the body and so is of low risk. Also remember that gamma radiation is very penetrating and so is able to escape your body very easily. In terms of a cost-free-benefit analysis, the benefit is almost always guaranteed to win. PET stands for positron emission tomography. A positron is a type of beta particle, though it's positively charged as opposed to negatively charged. In PET scans, patients are prescribed something called FDG, which is basically a sugar molecule containing radioisotopes of fluorine. As cancerous cells generally consume more sugar than normal cells, high concentrations of FDG indicate the presence of tumours, as shown in this image on the right as regions of bright colour. As we can see in this image, unfortunately there are bright spots in the rectum, the kidneys and the liver, which is most likely indicative of cancer. Moving swiftly on, we've now seen how diseases are diagnosed using nuclear medicine, but we can also use it to treat potentially deadly diseases. We've said that radiation has the potential to kill cells and damage DNA, and thus we want to avoid exposure to healthy tissue as much as possible. On the other hand, however, we can use radiation to kill cancerous cells, as is done every day, described as radiotherapy. There are two ways of doing this. Either you can fire gamma rays at target tissues from outside the body, or if it is preferred and an organ has a particular affinity for a certain element, such as the thyroid has for iodine, alpha emitters may be ingested, such as the use of iodine-131 to treat thyroid cancer.